Hello physics students. Welcome to our new topic called Gauss's law. And remember, in the last topic I mentioned this briefly already, that Gauss's law is another technique for finding the electric field of a certain charge distribution other than a proton or electron. And it's often, when it's applied correctly, it can get you the net electric field of a shape with far less headache and sweat than in the previous chapter. In the previous unit, remember what we did is we broke this object up into tiny little pieces that acted like a proton or an electron, and then we found the electric field by kq over r squared, and then we integrated to find the net electric field. And that was pretty difficult in some situations. So in this topic, we'll be using electric field of shapes, larger shapes, but with this thing called Gauss's law. It's a long topic. Just so you know, the test currently is scheduled, unless something happens, to change this November 6th, which is nearly a month away. Okay, so a big, long topic, lots of things to study in Gauss's law. Today what we're going to do is we're going to build the foundational ideas of what that are behind Gauss's law, and then we're going to I'll state Gauss's law, but we won't go into much detail other than just trying to understand the concept of Gauss's law. So the first thing, we need to review a math concept of a dot product before we can understand Gauss's law. We need to know the math solid. So today, electric flux and Gauss's law, this is a review of the dot product that we learned last year. Let me pause and give you a chance to jot this down. Okay, so you have two vectors A and B, and the dot product is defined as the magnitudes of them multiplied together times the cosine of the angle between the two. So most often we used this last year for calculating work. If we had force and displacement vectors with 0 degrees apart, that was a positive amount of work because we plug in cos of 0 here, we get 0. We get 1, and so it would just be force times distance. But if the motion, the displacement vector was this way and the force vector were that way with 90 degrees in here, you would get 0 work. Force vector dot displacement vector would give you 0. Even though force is not 0, displacement is not 0, those arrows, the product is 0. And then, of course, you could put 180 moving this way, force that way, and you get a negative amount of work. So multiplying vectors, more complicated than multiplying numbers. 2 times 3 is always 6 with numbers, with scalars. But 2 times 3 with vectors and a dot product can give you anything between 6 and negative 6, everything in between, okay? So you can also multiply the x components, the y components, z components, add those together. That's another way to do dot product. By the way, there's also a cross product. So with vectors, there's 2 ways to multiply. A dot product, which we'll be using for a good portion of the year, and then we're going to learn, when we get to magnetism, a cross product, a different way to multiply 2 vectors. All right, dot product. So now we're in the position to understand an important idea in physics, in electricity and magnetism, something called flux, okay? Flux is given this symbol. It's like an eye with a circle through it. And it's the electric field vector dotted with the area vector. In other words, electric field times area times cosine of the angle between the two. And you might be thinking, an area having a vector, a direction? I thought area was a scalar, length times width, like the area of this piece of paper. Well, not true. Area has a direction to it. Think about this. Maybe this is a patch of skin on a sunbather. They're standing up playing volleyball all day. They don't get a sunburn on their stomach. They lay down on the beach. Now they get a sunburn. The sun comes down. When it's beaming down on the surface, the illumination has an effect. It's the same thing with electric field. When the electric field runs along a surface like this, E is like this and the surface is like this, there's no flux. when it's like this, the electric field is hitting the surface, like kind of poking through it, there's flux. Now you might be saying, well, wait a minute. If electric field is like this and the area is like this, isn't that 90 degrees, cos of 90, 0? The area vector is defined. First of all, its length is the magnitude of the area. So the length of this area vector would be about, let's say, 0.2 meters by 0.3 meters. You know, if I measured them, 0.06. That's the length of the area vector. It's defined as always pointing perpendicular out of a surface. So as I'm turning the surface like this is how the area vector is turning. So now, when electric field comes and pokes through the back of this and comes out like this, so I have electric field lines going like this, that is flux, because I do this electric field times the area magnitude, 0.06 times the electric field, times the cosine of 0 degrees. I have flux. If I turn like this, the angle between the area vector, which is the pencil, and the electric field is now 90 degrees here, no flux when the electric field runs like this and the area is like that. So it doesn't poke through the surface. That's what flux is. But this formula only works if the electric field is a constant over the area involved. What if we have a lot of electric field up here and then it gradually gets weaker, for example? What electric field would we use? What we have to do then is perform an integral. We have to figure out the flux through a tiny area through which the electric field is roughly constant. Instead of dx, we use dA. So imagine like a little millimeter by millimeter tiny square right here. And I figure out the flux E times area in that. Then I add up all the fluxes for each little millimeter square along this entire surface. I get the flux of the paper. So that's an integration of flux through a tiny area. Adding up, adding up, adding up, adding up. Okay? So that's what flux is. Amount of electric field poking through a surface. All right, now, knowing that, we're now in the position to finally understand what Gauss's law is, this new tool that we're going to use in this unit for finding the electric field. You could, if I haven't already paused, I think I did, but in case I didn't, then I'll make a pause to allow you to jot that down. Okay, so let's now, I'll write out Gauss's law for you. The big idea, it is this. So, all right, so now, before I go into what it means, I just want to point out that every little symbol here is important. You remove one thing and your mathematical meaning will change radically. For example, if you leave this little circle off the integral, you're wrong. You're not saying the right thing. The circle, the vectors over the E and the dA, the dot in the middle means dot product, not later what we learned cross product. No, it's the dot product, okay? All that stuff people, when they, oh, we don't need that, I know what it is. No, you have to write it. I've used this example before, but when you're, a grammatical example, if I say, let's eat grandma, that's saying I want to eat my grandmother, right? Let's eat grandma. But if I say, let's eat comma grandma, I'm inviting my grandmother maybe for lunch. A little tiny little, oh, it doesn't matter, right? Oh yeah, it does, right? In terms of your meaning, you're saying radically different things. Same thing here, all those little symbols are important. So here's what it means. This means the net electric flux This is the translation, the net electric flux into or out of a closed surface. That's what all that means. Is equal to the charge enclosed by the surface all over this constant epsilon 0 I mentioned briefly in the last unit. It's 8.85 times 10 minus 12, and there's units involved. I don't want to get into the detail. I don't even have to write that down. We're just talking about theory right now. So it's just a constant. Okay, so that's what this means, a closed surface, not any surface, not like a piece of paper. Piece of paper doesn't work for Gauss's law. It's got to be something that traps a certain amount of space from the rest of the universe. Like, for example, this box. It can be what we call a Gaussian surface. Let me use it to demonstrate what I mean by, or how Gauss's law works. So here I have a special machine that blew up a proton. So here it is, the proton, right? Well, it's a little steel marble, but let's say it's a proton, right? So I take this and I close this box, so I've got a closed surface now, and I put the proton outside the box. What's the net flux along the surface of this closed box? Ooh, geez, that would be a horrendous calculation if you didn't know Gauss's law. You'd have to find the electric field vector, how it points in all the directions, how its magnitude changes, and you have to integrate over this surface, then that surface, then this one, that one, that one, over the 6 sides of this box. Whew, absolute nightmare. But Gauss's law tells me that since this charge is outside the box, it will create no net flux. Q enclosed is 0. The net flux is 0. Electric field going into the box here with an area vector pointing like this means negative flux. The cos is like 180. So I have negative flux from the electric field lines, well, I'm just going to roll away, going into the box. Those same electric field lines come out of some surface somewhere else over here, creating positive flux. Negative flux going in here, electric field going into the box, positive flux coming out here, no net flux. Gauss's law tells us the answer without any calculating. If, on the other hand, I put the proton inside the box, okay, what's the net flux coming into or out of this box now? Well, first of all, we can kind of sense the flux is positive because the electric field is coming out of the proton, so it's going to be coming out of the box surfaces on this side, that side, this side. All the sides the electric field is going to be poking out, and the area vector is poking out. EDA is a positive number integrated, so it's positive. But again, if you didn't know Gauss's law, calculating, we could say, oh yeah, there's going to be positive flux now, but to get the numerical value, that would be another nightmare. Finding the dot product of the electric field, which changes throughout, the direction changes around, you have to integrate around all these sides. I don't even want to think about doing that. With Gauss's law, it's easy. The answer to this, 1.6 times 10 to the minus 19th positive for the proton, divided by that constant, 8.85 10 to the minus 12, boom, you get the answer without just dividing on a calculator. If I put an electron, then I just put minus here, because the electron would be drawing the electric field into the box. That's now E, dA, negative flux. And we could just divide, we get the flux of the electron. It also doesn't matter the shape of the box. Would I get a different answer if I put it into a cylinder, a closed cylinder? First of all, oops, it's a little loud. Right now that's not a Gaussian surface because it's open here. Has to be closed, right? That's what this circle means, closed. I close it now, seal it up, and then I could now calculate the flux coming out of that box if it's a proton. Same answer as if I put it in a box. Doesn't matter what the shape of the box or the 3D surface is. So that's the concept of Gauss's law, and we'll be applying it for the next month. But today what I want to do is just do some examples of calculating flux, okay? So kind of back off a little from Gauss's law and just calculate flux. So I don't know if I paused, so if I didn't, then I'll pause now. give you a chance to jot this down. Okay, so example 1. Okay, so there's the example. We've got an electric field that's got 5 in the x direction, 6 in the y direction, and -3 or 3 in the negative z direction. That's in that notation. So it's in 3 dimensions. And I want to find the flux through a rectangle in the xy plane. So this is just the xy plane. Of course, it extends further in all directions. And so what I have is an electric field. If I have, say, x going like this, so that's maybe I hat. See if I can make it look like it's on the surface. This is j hat. Oops. And then, let's see, x, y, z would go like this. K hat coming out. So there are my coordinate axes. This electric field has 5 in the x direction, 6 in the y direction, and then 3 down like this in the negative z direction. So 3 going down like that. And then my surface is 3 by 4 meters. It doesn't really matter which way it's oriented as long as it's along the plane here. So maybe this is 4 meters. And then 3 meters over here. Okay, so there's my surface. So rather than getting very picky with the notation of putting in dot products, what I could just say is this. I could say that the flux is E vector dot area vector. And just using common sense, I could see that the 5 and the 6 do not create flux because they're running along the surface. The only one that pokes through the surface is the 3 pointing into that surface. So I could take that electric field, -3 newtons per coulomb, and then multiply by the area, which for a rectangle, of course, is just 4 meters by 3 meters. Okay. Which is, flux is -36 Newton meters squared over coulombs. Let me pause to give you a chance to catch up if you need it. Okay, so the minus sign is actually not all that critical here. It's more important when you're dealing with a closed surface, the minus sign indicating electric flux going into the surface, positive coming out. So, but just as long as you know how to get the numerical answer, that's good enough. Let's take a look at a second example. So just E times area is what we did there. This one, let's see. Oops, ran out of space. So we've got an electric field now that varies. It's not a constant, it's a function, but it's in the z direction, and we want to find an electric field through a certain electric flux through a certain rectangle. It'll become clearer when I sketch this. So here's my x-axis, there's my y-axis. So the rectangle is between 0, 1, 2, and so from here to here, and then between 1 and 3 along the x-axis. 1, 2, 3 right here. So it's actually a square. So through that rectangle, I want to know the electric flux, okay? But here's the thing. As I said, it varies. And it's coming out of the board, by the way, because it's in the positive. Well, actually, at 1 meter, if I plug in 1 here, I got 6 minus 3 times 1 squared, in other words, 3. The electric field is 3 at this x-coordinate. So what I could do is maybe I'll draw some circles like this. To indicate the electric field. Remember an arrow that points straight out of a surface? When we're drawing that three-dimensional idea, we draw a dot with a circle around it. That represents, like if I had an arrow pointed straight at your eye, you'd see the shaft like this and the point of the arrow. Those are those electric field vectors pointing straight out. If I shoot an arrow directly away from your eye, as it's flying away, you'd see the feathers. So out or into the board, an arrow shooting that way into the board, you draw a circle, and this is like the feathers of an arrow. So just a reminder. So at radical 2, which is 1.4, somewhere around here the electric field is 0. Then at 2 meters, if you plug 4, negative 12, so it's basically then here it's going to be negative 6. So the same magnitude electric field like this, I try and draw the same size arrows going into the board. Okay. And then as I gradually move to more and more positive x, the electric field becomes more and more negative. In fact, at 3 meters, we've got negative 21. We've got a very large electric field going into the paper here. And maybe something in between like this at this x-coordinate. So this is just to get us to visualize this and understand, but it's actually not necessary to draw something like this. So we want to find the flux through that surface. How can we do it? Well, we can't use E times area. But we can use the concept of E times area. If we pick an area, a small area, over which the electric field is roughly a constant. So we could say the D flux, the flux through a little area, would be, if we pick the area correctly, it would be then E dA. Or maybe I'll do the E in white. So what area can we pick so we could use that? We have to pick an area that goes oriented like this. Skinny, a thickness dx, and a height from 0 to 2 meters. In other words, 2 meters tall. So I could say that the flux in that skinny shape is the E 6 minus 3x squared times that area, which is length times width, 2 dx. Okay? That's the flux through here. Now, by the way, making the rectangle this way, no good, because notice the electric field is varying along that surface. We couldn't say E times area. Only when we go like this, we have the same electric field along the area. Sometimes you make the area go this way. If it were a function of y over here, we'd make the area go this way. But I don't want to get into that too much. Let's just continue on with this. So that's the flux through this rectangle. Now what we want is the total flux through the whole square. What we'd have to do is add up all the flux through every little rectangle, starting here and ending there, from 1 to 3, adding up. So how do we add up little tiny things? Once again, we integrate. And we began, as I said, starting at 1 and ending at 3. And we could say 2 So now I just have to evaluate the integral. So the 2 stays constant. This 6 dx integrates to 6x. And then 3x squared integrates to 1/3, 3 1/3 x cubed. Right? Add 1 to the exponent and then divide by that new exponent. So those go away, and now I just plug in my limits and solve. Oh, maybe I'll do a bracket. So this is 5 over here, and then we've got -9, -14. All right. I get -28, and of course the units would be Newton meters squared over coulombs. But maybe I made a mistake. It doesn't matter. You know, the number's not important. You just punch it on your calculator. But that's how you do it, okay? So recap, what we do is we arrange the rectangle in such a way, the skinny rectangle, so it captures a constant electric field through it. That means it's going to be a height of 2, a width of dx, and we do E times that area, 2 times dx, and that's the flux through there. And then we integrate over the entire shape. That gets us the flux over the entire shape. There it is. All right, so let me pause and give you a chance, if you need it, to jot the rest of this down. Okay, long notes, but I do want to do just one more example. So I guess I'll do here. Let's see, I think it was a 2 meter. All right, so x Well, maybe not doing so well projecting the X down, but okay, well, won't waste too much time. All right, so there's my cube, 2 meters by 2 meters by 2 meters. At the origin, here's my electric field. So I want to know the net flux into or out of that cube, okay? So the first thing I want to do is tackle the y direction flux. We've got 3 electric field in the y direction pointing along this surface, 3 newtons per coulomb right there. And out this surface, we've got also, 3 newtons per coulomb. So, for that pair, let's call that the flux parallel to the xz planes. Right? These are all in the xz, parallel to the these 2 surfaces. What I will get is I have to take the flux here and add to that the flux here. But here's the thing. So I have to add this flux and that flux. This flux here at y equals 0 is negative because the electric field is going into my box. So this is some negative quantity. This flux is positive because it's coming out of the box on this surface. The electric field's coming out of this cube over here, in here on the back, out on the front side. So that means this flux is positive. Furthermore, we have the same electric field over the same area, so we get 0 for an answer for these 2 surfaces, okay? And then we could say it's basically flux equals 0 for each parallel pair. So without any calculating, we could just reason out our understanding of flux, that the net flux through the entire cube is 0. It doesn't mean it's 0 on all surfaces. It's non-zero on these surfaces. Non-zero on these, but they add to 0. And then the final example, determine the net charge enclosed in this cube right here. And you might be saying, well, wait a minute, they didn't tell us anything about any protons or electrons anywhere in this problem. Here's where we could use Gauss's law. We know that the net flux, which stated through Gauss's law, we could write this I with a 0th, or we could write this. This is the net flux through this closed surface, is Q enclosed over epsilon 0. We just figured out the flux is 0. And so that means epsilon 0 is not 0. That means Q enclosed has to be 0. It doesn't mean that there's no charge in there. It just means the net charge inside the cube is 0. For every proton in this box, there's an electron matching it, creating a net Q enclosed of 0. So, probably a pretty long video, a lot of important ideas. Actually, I got to pause and give you a chance to jot this down. Okay, so again, we learned about flux, more important than getting bogged down with the ideas of dot products is the concept that it's electric field going through a surface. Flux, no flux, okay? That's the important thing. And then we learned how to calculate flux, either just E times area cosine of the angle, or we had to integrate if the electric field varied over a surface. And then the big idea, Gauss's law, the net flux into or out of a closed off surface that's closed off, the net flux into or out of this surface is equal to Q enclosed over epsilon 0. All right, so that's it for today. We'll move on in the next physics video to using Gauss's law to actually determining electric field, the big utility. Okay, so see you in that video.